Good morning class and welcome to another lecture in energy storage technology. So we will continue our discussion on various types of energy storage technology, and we were covering electrical energy storage systems, primarily capacitance based energy storage systems. In the previous class we discussed electrolytic capacitors, which have specific metal anodes. The positively charged plate is made of special materials like aluminium, tantalum, niobium, etc. with high dielectric capacity, aluminium, tantalum, niobium, etc. which when undergoing the anodization process creates thin layers of rough oxides on the surface of the metal like aluminium oxide, tantalum oxide and niobium oxide, which have high dielectric constants of 10, 26, 42 respectively, which increases the capacitance of these electrolytic capacitors. We saw that because of the high dielectric constant as well as the high A by D ratio, the contact area versus dielectric thickness ratio is very large, because the oxide layer is quite thin, in the order of maybe a millimeter or a half a millimeter like that, and because the oxide layer is rough, so the contact area is larger and the contact thickness is smaller, so A by D ratio is very large, and that creates higher capacitance values for these electrolytic capacitors. We also saw that the rest of the distance between the cathodic plate and the dielectric metal oxide is filled up by some electrolyte which is able to transmit the negative charges to the surface of the dielectric oxide material. And this electrolyte can be a liquid, can be gel, or can be a solid which can create polymeric bonds with the metal surface to ensure good contact. So for such systems, the total capacitance, that is the dielectric constant into vacuum permittivity into A by D, is of the order of 10,000 microfarads. That is of the order of 0.01 farads, because 1 microfarad is 10 to the power minus 6. So 10,000 microfarads is around 10 to the power minus 2 farads. Okay. So that is the capacitance that you are getting for these kinds of systems. Okay. So you can contrast this with the traditional capacitance values of traditional capacitors, where the values are relatively low, around 100 microfarads. So we are getting at least 100 times greater capacitance values because of the presence of this dielectric metal oxide on the surface of the anode material. So one of the advantages of a higher capacitance is you are getting higher energy storage abilities. Okay. One disadvantage we discussed is that the electrolytic capacitor is asymmetric. That is, the anode metal and the cathode metal are different, and the metal oxide is only on the anode metal side. So you have to have a DC source to keep the voltages, keep constant voltage polarity between the two metal plates. If you are running an AC current, then the polarity will be changing with the phase, and that will lead to breakdown of these types of capacitance. So I couldn't cover in the last class the total energy content that you can carry in these kinds of capacitors. So if you assume that the rated voltage is around 40 volts and the capacitance is 10,000 microfarads, then one capacitor plate will store around half CV square. So C is 10 to the power minus 2 farads, because that's 10,000 microfarads, and the voltage is 40 square. So what you will be getting in this case is around 8 joules of energy. So you can compare this with a traditional electrostatic capacitor with ordinary metal plates. There you are getting half a joule of energy. Here each plate you are able to generate around, you are able to store around 8 joules of energy. So that kind of shows why electrolytic capacitors, even though it still is storing less energy than say other types of energy storage media, like we discussed compressed air energy storage or water energy storage, in terms of capacitance, it is 16 times higher energy storage capacity than traditional electrostatic capacitors. So they have small specific energy like still larger than the traditional capacitors, but still small specific energy of 0.03 watt hour per kg. However, its specific power is large, around 1000 to 10,000 watts per kg, as we discussed, and this can be charged and discharged at very fast rates and can withstand very fast cycles. So, and they have high round trip efficiencies as well. Okay. So, so these capacitors are ideal when large amounts of electric power is required, like the startup of heavy electrical equipment like compressors, pumps, etc. And they can also be used to compensate for rapid spikes in the demand and the supply matching in a renewable energy grid. Okay. So those two applications are specifically good for electrolytic capacitors. So that was the previous discussion on the second type of capacitors that we covered. In this class, we will discuss another type of capacitor, which is the super capacitor or ultra capacitor, which has been developed only in the last 2 decades or so, and it is providing much higher amount of energy storage ability. So it has very high specific energy of 5 watt hour per kg. So you can compare this with electrolytic capacitors, which have specific energy values of 0.03 watt hour per kg. So this is like more than 100 times, like almost 100, around 100 times that of electrolytic capacitors. So super capacitors have specific energy densities more than 100 times that of electrolytic capacitors. Okay. They are also called electric double layer capacitors, EDLCs. We will see why they are called this electric double layer capacitors, EDLCs. They have very high capacitance. So see, the capacitance values are varying from 1 to 5000 farads. Okay. So the key advantage of supercapacitors is their extremely high capacitance value. You have capacitance values of 1 to 5000 farads, whereas for electrolytic capacitors it was around 10 to the power minus 2 farads, and for traditional electrostatic capacitors it was like 100 microfarads, like 10 to the power minus 4 farads. So we are getting once again 100 to 1000 times increase in the capacitance value in supercapacitors compared to electrolytic capacitors, and that is directly transferring into the high specific energy availability that you are seeing. Okay. However, the disadvantage is the maximum voltage that can be sustained across these capacitors is quite low, around 1 to 3 volts. So this is in contrast with traditional and electrolytic capacitors, where you can get up to 40 volts of potential difference between the two plates. Here the potential difference between the two plates can at most be 1 to 3 volts. So what is the principle of this electric double layer capacitor? So first let us look at the figure. So this is one end, the anodic end of your capacitor. Okay, so you have the positive charge here, and here there is no metal oxide layer, and the electrolyte is in direct contact with the anode. Okay, so this entire section is the electrolyte. It can be an aqueous electrolyte, a gel electrolyte, something that can transport the negative charge to the surface of the anodic plate. Okay. So now there is no oxide layer. So how is the dielectric being sustained? So what happens here is that at low potential differences, when the potential difference is below 3 volts, right, or 1 volt for aqueous solutions, a small layer, a single molecule layer of electrolyte gets trapped between the positive charge of the anode and the negative ions that are in the electrolytic system on the anode surface. So this single molecule layer of polarized electrolyte molecule that is getting adsorbed into the anodic plate. So the anodic surface is porous, okay, and the porous anodic surface is adsorbing a layer of this electrolyte, a single molecule layer of the electrolyte on its surface, and that adsorbed layer of electrolyte is separating the negative ions that are present on the on the electrolyte and the positive charges that are collected on the anode surface. Okay. So you have a single molecule layer of electrolyte separating the two charges, and this single molecule layer is basically what is acting as the dielectric. Okay, so this is what we have discussed here, that we have a conductive electrode which is placed in contact with an electrolyte. Okay, the conductive electrode is the anode in this case. It can also be the cathode, and we will see that the cathodic end as well in the complete figure. Then a double layer of charges of opposite sign are formed. One layer forms on the electrode surface and the other layer forms on the electrolyte, the positive charge and the negative charge. Between these two charge layers, we have a single thin layer of solvent electrolyte molecules that adhere to the surface of the electrode and act like a dielectric of a conventional capacitor. So this single molecule adhere or adsorb on the surface of the electrode and act like a dielectric, separating the two charges of a conventional capacitor. Okay. Now the thickness of the charged layer, this charged layer and this charged layer is around 0.1 nanometers. It's very thin. Nanometer is 10 to the power minus 9 meters. So this is 0.9 nanometer is the thickness of the charged layer on the electrode, this value, this layer here. Okay. And the thickness of the solvent dielectric layer and the ionic layer in the electrode, so these two together is 0.1 to 10 nanometers. Okay. So this thickness of the adsorbed electrolytic molecule and the ionic charge, these two layers together is thickness is around 0.1 to 10 nanometers, and the charged layer is on the electrode surface is 0.1 nanometers. So the total thickness is 0.1 to 10 nanometers. Okay. And of this, so the total length together is 0.2 to 10 nanometers, 0.2 to 10 nanometers, and this length, this thickness of the electrolyte molecule and the charged ion together is called the Debye length, okay, which is 0.1 to 10 nanometers. So part of this is the solvent molecule, which takes up most of it, and the rest is the negative ionic charge. So clearly the thickness of the electrolyte is around 0.1 to 10 nanometers only, right, 0.1 to 0.9 nanometers only. So the electrolyte layer, which is acting as the dielectric, is extremely thin, right, 10 to the power minus 8 meters. That is where we are looking at 10 to the power, 10 to the power minus 8 meters or 10 to the power minus 10 meters. If it's 0.1, it's 10 to the power minus 10 meters. If it's 10 nanometers, it's 10 to the power minus 8 meters. Okay, because 1 nanometer is 10 to the power minus 9. Okay, so you have a very, very, very thin dielectric layer here. Okay. So the very low thickness and high surface area, example nanoporous carbon electrodes. So typically here you get porous electrode material is used on which the solvent electrolyte can be adsorbed. So because it's a porous electrode like a nanoporous carbon, you have a lot of surface roughness. Okay, because of the porosity and all of that, the net surface area over which the solvent molecules are getting adsorbed is quite large. So the surface area of contact of the dielectric material, which is the solvent molecule, adsorbed solvent molecules here, is very large. So you have a large A value and a very small dielectric thickness value. This D is basically this one here, 0.1 to 10 nanometers here. So this is of the order of 10 to the power minus 8 to 10 to the power minus 10, and this surface area is quite large because of the porous electrode material that is used. Okay. So this together then means that the capacitor units, the capacitance unit values that we get, which is the epsilon into epsilon naught into A by D, that becomes on the order of farads. So 1 to 400 or 500 farads. So that's what you are getting. Okay. So you are getting a very high capacitance value because of the high surface area and the low thickness of the dielectric single molecule layer of electrolyte that is serving as the dielectric here. Okay. However, we are actually not using a what is called a insulator or a material that is very good at separating charges or preventing charges from being transported through it. Okay, we are using an electrolyte material only. So your potential difference across the electrode plates cannot be very large. It can only be around 1 volt for aqueous materials and for non-aqueous organic electrolytes it can be 2 to 3 volts. So contrast this with 40 volts of potential difference can be sustained across traditional dielectric materials as well as alumina, niobium, tantalum based dielectric materials. So here, because we are not using a dielectric material, we are using the solvent itself as a charge separator, the voltage gradient cannot be more than 2 to 3 volts. Okay, so that is one disadvantage here, because beyond this threshold potential difference of 1 to 3 volts, the polarized electrolyte molecule begins to undergo electrochemical decomposition and can no longer function as an electrolyte. So the electrolyte molecule itself will start breaking apart into positive and negative ions beyond this potential gradient, and hence can no longer function as a dielectric separating the charges. So that's why you have a smaller potential difference. Still, the total energy is half CV square and capacitance is 1 to 5000 farads, voltage is 1 to 3 volts. Okay. So suppose we take the voltage as 2 volts and the capacitance as 5000 farads. So this becomes half into 5000 into 2 square, that is 4. So this becomes 5000 into 2, so 10,000 joules. So electric double layer based capacitance system is storing on its plates 10,000 joules of energy. Okay, this can be compared to the previous case in electrolytic capacitors, where the energy content was much lower. You are getting around 8 joules, 8 joules here. Okay, and for the electrostatic capacitors is half a joule. So half a joule, 8 joules, 10,000 joules. So we are getting 1000 to 10,000 times increase in the ability of ultra capacitors to store energy compared to even electrolytic capacitors. Okay, so that should be clear. Now the supercapacitor itself will have a positive electrode here as well as a negative electrode here. So you have an anode and a cathode, and you have electric double layers being formed on both sides. On the cathodic end, you have negative charges on the surface of the metal, positive ions are being transported to the surface of the metal, and in between the positive ions and the negative charges, you have an adsorbed layer of electrolyte that is acting as the dielectric. So the same principle, except that the charges are different. So here the metal has the positive charge, on the right in the cathode the metal has the negative charge. Here the electrolyte has the negative ions, here the electrolyte has positive ions. Okay. So a supercapacitor consists of two electric double layers in series connected by an electrolyte and having a separator in the middle to allow ions to move but not electrons. So this separator ensures that positive and negative ions can move to the either side and get accumulated, but it does not allow electrons to move. Okay, so it prevents the leakage of positive and negative electron charges but allows the free transport of electrolyte ions. Now, if this is the case, and if the capacitance on the anodic side is C1 and the capacitance on the cathodic side is C2, then the total capacitance is C1 into C2 by C1 plus C2. Okay, so this is the total capacitance of one complete supercapacitor, C1 into C2 by C1 plus C2. If you have a symmetric capacitor, then it becomes C1 equal to C2 equal to C, so C total is C by 2. Remember, the reason why we have to include both is there are two dielectric materials here, and basically you have two capacitors here, positive charge, negative charge dielectric one capacitor, positive charge, negative charge dielectric second capacitor, and this is forming because you have two metal plates and the local capacitance is happening on the proximity of these plates itself. Okay, you don't have one double layer of charge separated by a dielectric, you have two double layers of charge and you have to account for them both. So that is why this is the total capacitance of the superconductor, and if it's a symmetric capacitance, the capacitance on both sides is the same, then the total is C by 2. If it's an asymmetric capacitor, then C1, if it's much greater than C2, then the total capacitance is C2. Okay, so there is a decrease in the capacitance value due to the presence of these two double layers. Now, what is the property of these types of ultra capacitors? So the cycle time can range from 1 to 100 seconds. So these capacitors can store energy around 1 to 100 second cycle time. So it can withstand cycle times of 1 to 100 seconds. So these are also withstand very fast charge discharge cycles. So cycle times of 1 to 100 seconds it can withstand. Okay. It has a reasonably low self discharge time of 0.2% per hour. So it is possible to have these types of capacitors store energy for several hours or days without losing a lot of the energy in the process. It won't. The lifespan of these energy storage lifespan of these capacitors is not over a month, but if you think of diurnal energy storage, then the loss is not significant. Okay. And the cycle lifetime once again is in millions of cycles. So these are extremely stable capacitors. With cycle, it can withstand millions of cycles before the capacitor property decreases enough that it has to be thrown away. The cycle efficiency is around 0.95, so again very highly efficient. The specific energy is 5 to 9 watt-hour per kg. So as we discussed, it has a high specific energy, 5 to 9 watt-hour per kg. How much energy it is storing per kg of the capacitor material. And your specific power is very large. As we discussed, capacitors in general can transmit and absorb electricity at very high rates. So the power transmission and power absorption rates are quite high. So the specific power is 3 to 10 kilowatts per kg. So that's the rate at which 1 kg of ultra capacitor material can absorb or transport electricity to and from a grid. Okay, so it's a very fast responding capacitor with good cycle life, very good cycle life, almost unlimited cycle duration, very good cycle efficiency, very good specific energy, and very high specific power. It can transmit the charge electricity at very high rates. So supercapacitors have many advantages, okay, and are beginning to replace rechargeable batteries in several applications. Okay, so they have high energy density, fast charge discharge times, good cycle times. So they are beginning to be quite widely employed in many technologies and are even replacing rechargeable batteries. Batteries we will come to next, but it's beginning to replace batteries in several applications. They have very high peak currents. One of the advantages, high peak currents can be achieved. Low cost per cycle, because a supercapacitor lasts for millions of cycles. On a per cycle basis, the cost is quite low, even though actual cost is higher than that of batteries. Okay, there is no danger of overcharging. So this is just a electrostatic energy storage device, and if the voltage potential increases, what will happen is charges will start breaking down the dielectric single layer of material. Okay, then what happens? The capacitor stops working. But there is no danger of like explosions, safety hazards, etc. if you are overcharging a capacitor. Okay, so it has better operational safety, low material toxicity, and non-corrosive electrolytes. So the type of material these capacitors are built from does not have any toxicity associated with it. Neither does it need non-corrosive electrolytes. Okay, so there is no specific requirement of having non-corrosive electrolytes to get these capacitors working. Okay, and does not require complex electronic controls and switching systems. It's very safe, easy to control, so does not require a complex controlling system, and it has very high energy density, high peak currents, low cost per cycle, and all of these advantages. Okay. Now, one problem with supercapacitors is its voltages are often too low. In actual utilities, you need somewhat higher voltage. Okay, so what we do is we connect these capacitors in a series parallel format to increase the total voltage output from the capacitor array. Okay, so a supercapacitor cell consists of a series of supercapacitors that help increase the voltage. A supercap cell consists of a series of supercapacitors that help increase the voltage. These cells are then connected in parallel to increase the capacitance. Okay, so we will see what this means. So here we have multiple supercapacitor cells. So this is the say anode, cathode, anode, cathode, anode, cathode. This is the electrolyte in between, and you have 1, 2, 3, 4, 5. 5 capacitors that are connected in a single row, and you 2 connectors in a series. So there are 2 series and 5 rows. Okay. So each individual capacitor, let's assume, has a cell voltage CV and a cell capacitance CC. Okay, so the voltage across a capacitor is CV and the cell capacitance across the capacitor cell is CC. Okay, so the total voltage is cell voltage into number of rows. Okay, so that's the total, that is the cell voltage. The total cell voltage of individual capacitors and the number of rows. Okay, so the total voltage is cell voltage into number of rows. Now the cell voltage we can say is 2, say assume it's 1 to 3. So suppose it's 2 volts. The capacitor cell voltage is 2 volts and the number of rows is here 2 rows. So 2 into 2, that is 4. Okay. So here cell voltage, say it's 2 and the number of rows is 2, so it's 2 into 2, 4. If the cell voltage is somewhere different, say 1 volt, then it's 2 into 1, 1 volt. Okay, 2 into 1, 2 volts. Okay, so by adding more rows, you can increase the total voltage out of this array. So suppose instead of 2 rows, you are having 4 rows and the cell voltage of each of these cells is 2. Then the total voltage output from the 5 rows is 2, which is the cell voltage, into 5, that is 10 volts. Okay, so that's the idea. Then the total capacitance that you are getting out of this array is the cell capacitance. What is the capacitance of each cell into number of rows by number of columns by number of rows. So here you have 5 columns and 2 rows. Okay, just like a matrix. So the cell capacitance into number of columns by number of rows. So it's Cc into 5 by 2. Okay. So it has 2 rows, so 2 Cv, and here it's 5 columns, 2 rows, so 5 by 2 into Cc, which is the cell capacitance. Now suppose your cell capacitance is 1 farad and cell voltage is 3 volts. Instead of 2 volts, you have 3 volts, right? So then this is 2 into 3, 6 volts. Correct. And here it's Cc is 1 into 5 by 2, so 2.5 farads. So the cell capacitance, the total capacitance of the array is 2.5 farads and the total voltage of the array is 6 volts. Okay. So that's the idea. Okay. Then the total energy stored in the array is half C into V square. Half into 2.5, the total array capacitance is 2.5. And voltage is 6 square, so it becomes 45 joules. Okay. So while suppose you instead you have a single cell, then C was 1 and the voltage was 3. Okay, so half into 1 into 3 square. So 3 square is 9, 9 by 2, so 4.5 joules. So we are getting 10 times increase in the energy storage in that array. Okay, so that's the idea. Okay. So further research in the electric double layer capacitance is going on. Recent work has resulted in supercaps with graphene electrodes. So instead of regular carbon nanoporous electrodes, you are using graphene electrodes with 80 watt-hour per kg energy density. So even more energy density than previously. And 4 volts operational potential difference. So again, another boost to the total energy storage that can be done in these capacitors. Supercapacitors are currently present in cell phones, DG cams, etc. to provide power for flashlight as well. So one place where supercapacitors are used is when you are turning on your cell phone and turning on your cell phone flashlight button, the flashlight of the cell phone comes up, and the flashlight of course is utilizing a lot of extra electrical energy. So that is coming from a capacitor system initially. Okay, from the battery to the capacitor, and capacitor can transmit power at very high rates, remember. Okay, so that is the advantage. Because the flashlight consumes power at a very high rate, a capacitor is utilized to transmit that power to the flashlight. Similarly, in cell phones, often when you are in roaming mode, you are trying to search for signals. Different types of 4G signals, Wi-Fi signals when you are on the in a journey. Okay, so finding signals also require a large power expenditure. So there also a cell phone uses a capacitance based system to get that power out of the primary battery. Okay, so it gets the power out of the battery, and then the capacitor stores that power and releases power at a fast rate to run a Wi-Fi search or an internet provider search, or producing light for your camera or cell phone flash cam. Okay. Also, in many places, the regenerative braking technology of cars and even trains are being used, are places where supercapacitors are used. So again, if you remember what regenerative braking technology is, when the car or a train is braking, part of the energy that is lost during braking, part of it is stored in the capacitance system. And then when the car is again accelerating from the braking position, it requires an extra boost in energy. So that extra boost is coming from your ultra capacitor. Okay. So in regenerative braking technology of cars, ultra capacitors are present, absorbing energy at a fast rate when the car is braking, and then releasing energy at a fast rate when the car is accelerating. Okay. And this is true even for trains. Usually flywheels are used in this context because flywheels can store significantly more energy than traditional capacitors, and trains being heavy require a lot more energy than a car for its braking and acceleration purposes. So flywheels are usually the technology of choice, but ultra capacitors have significantly increased in its energy density, and hence is beginning to replace flywheels as a preferred way of storing and releasing energy at a fast rate for braking and accelerating purpose in trains. Okay. So that kind of completes our discussion on electrical energy storage systems. We talked about three basic types of capacitors: the traditional electrostatic capacitor, relatively modern electrolytic capacitor, and a very modern ultra capacitor, where in the ultra capacitor case you are getting much better specific energy density, much greater stability, so it's beginning to replace battery in many of the applications. Okay. So thank you for listening. In the next class we will start our discussion on battery based energy storage technologies. Thank you, and see you in the next class.